Screen is visible, right? Okay, welcome back all the participants. I would like to give introduction about Dr. Gopalakrishna Hegde now. Gopalakrishna Hegde received his MSc and PhD in physics in India. Sorry. He is currently faculty with the Biosystems, Science and Engineering and Aero Department, Indian Institute of Science, Bangalore. He was an associate professor in UK Open University, Singapore, and research director at the NPAEM Center of Innovation, Singapore. He has over 90 research publications in international journals and conference proceedings and has granted 6 patents. He has guided many MS, MTech and PhD students. He has taught various courses in physics, photonics and nanotechnology at undergraduate, postgraduate and PhD levels. He is a member of Board of Management, Board of Studies, academic boards of few universities or institutions in India. He has presented invited talks, keynotes at various institutions and at international conferences. He has been a technical committee chair, advisory, review, organizing member of many international and national conferences. He has been a reviewer for many international and national journals. He has completed many sponsored research projects in India and in Singapore. He was a consultant to many industries in Singapore and India. He was visiting professor, scientist in the Femto ST Institute, University of France, University of Rennes, France, University of California, Law USA, and La Trobe University, Australia, NP Singapore. His current research interests are in the areas of photonics, nanophotonics, optomicrofluidics, optical sensors, photovoltaics, integrated optics, optical flow diagnostics, and photonics education. He is a performing artist of Yakshagana, a classical folk dance of Karnataka, tabla player, Hindustani. Okay, so this is about Dr. Gopalakrishna Hegde. We are welcoming you, sir. Over to you, sir. Please take over the session, sir.
Can you see the... Okay. Hello, can you see the slide now? Hello?
Not yet, sir. Please share it, sir. Please, once again, click on the sharing, sir.
1 minute. Slides are not seen now?
I'm not seeing, sir.
1 minute. Now?
It's not sharing. Once again, click on stop sharing and share it once again, sir. Oh, yes,
Now?
sir. It's visible, sir, now. It's clearly visible.
Oh.
Yes, sir.
Good morning to you all. Let me start. The title which I gave was Photonics Components for Quantum
Full screen,
Application.
sir, if you don't know.
Can you hear me now?
If you can hear, sir, make it full screen, sir.
1 minute.
Yes, sir.
Okay.
Yes, yes. Thank you, sir.
Yeah. Thank you for the introduction. And let me start. Okay. The title I gave was Photonics Components for Quantum Applications, quantum computers, or whatever it is. Basically, I'm not a researcher in quantum. My research field is mainly photonics. Definitely, photonics is the backbone for any quantum we talk about. That's what I can say. But many of my research in photonics definitely lead to some applications in quantum area. That's the first thing, and I think Dr. Srinivas has given a good talk, and he talked a lot of mathematics and basics of quantum computing. Definitely many of the concepts or many of the slides which he shared may be overlapping here and there. And as you all know, quantum computing or quantum still in developing stage, even though many of the companies claim that, like IBM says that they are already quantum computers working, and even Intel is telling they have fabricated many of these quantum computing related components, etc., etc. Definitely in India it is nowhere, and even the government is pushing for quantum. I think some initiatives have been started that is yet to in a very very infantry stage of demonstrating qubits and these kind of things. And here and there they say that they have demonstrated the free space quantum communication, etc. A long way to go, but let us start some basics, the ideas which are coming and what may be the future. I will try to touch upon these things. Definitely have taken slides from internet here and there. I think you will see all these things. And if you look at the future of computers and this Moore's law, what it says, the the this graph shows, okay, the transistor density, and these the circles which show the uh, dimensional reduction in silicon chips, okay. And minimum future size, we call it as, this is the transistor density. Okay, look at the way it is in 2015 maybe. uh, it is about 10 to the power 7 transistors per millimeter square. And if you look at the minimum feature size, okay, I have extended this one. If you look at, okay, this is the minimum feature size, and still going down here somewhere here. This graph is here. Look at, now we are hitting somewhere here. The 20 is about 10 nanometers, and many of the foundries like IBM or Intel, they all claim that they have already successfully fabricated 10 nanometer gate, 15 nanometer, 20 nanometer. And ultimately what we are going to hit is about 1 nanometer, and ultimately this is the target. It is about 0.1 nanometer. When you say about 2030 or 2020, if we are able to make 10 nanometer successful processors, and if these computers are maybe on the table, then maybe 2030 or the 40 or 2050 we may hit a 0.1 nanometer. I don't know where this graph will go. I think if you look at this trend, I think this is almost saturating here. Okay, so this graph is saturating. I think definitely we have hit upon now to practical. Okay, this is where the basic transistor, and this is the gate length they talk about. Reduction is coming from here, and if you look at the way we are seeing the speed and the memory of the computers, I think this has become stable right now. You don't see any more high memory computers, high speed processors like that, because we have hit this stage. Now ultimately where we go to, when we go to 0.1 nanometer, we will be here somewhere. So all this here, this is called classical computers, where we exploit the motion of electrons in the crystal. Whereas when we come here, we are hitting the atom, then we'll be playing with the electrons within the atom. So this is where quantum comes. Okay, uh, my whole talk will be on the physics part of it. Not I'm going to the engineering part of it. I will touch here and there. Okay, this is where actually atom, and you'll be manipulating these properties of atom. Okay, and that is ultimately the electron transition that leads to quanta, it's a photon. Okay, so I don't know still why people call it quantum properties you are exploiting. That's why it is a quantum computing. That means the atomic process is a quantum phenomena. So that's where we stand in. I think you can read some of these articles, fantastic articles. This is where the quantum computing comes. Okay, most of will still run into, that's what I explained, will soon run into major physical constraint. This is a physical constraint. Okay, so when we hit here, then whatever the concepts or the theories of physics what we are using, that may not be useful anymore, and you will be going here quantum. You have to explain everything in terms of quantum. That's then the quantum communication, quantum computing, all they are coming now. Now, this is limitations with classical computers. That's what I just explained. Okay, this is some security terminology. Okay, 100,000 computers in parallel and 3 gigahertz processors at factoring would take longer than the age of the universe. These are all the issues the scientists talk about, and I think this is the common slide everybody share. That's where this great scientist Feynman talked about is quantum simulation. It is inefficient with classical computers. Okay, why not use quantum mechanics for computation? This is where he predicted in something somewhere 1960s. I think that's where we. I think even if you go to nano technology also, we follow the same concept which he proposed, saying that there are lot of opportunity at the bottom, and the same thing is leading to quantum computing. I think this is real. I think that's how the science, the physics goes. So we may talk whatever today, we may that may be real after 20, 30 years. And I think this has taken a long time. Now he's talked about in 1960s, and I think that's what we are really realizing now. It is about 60 years now. So now this is where the quantum computers fundamentals applications, anybody can read these books or whatever it is, and whole quantum computing is dependent on this concept. Okay, that's where function mathematical explanation. That means in this quantum sphere there are n to the n power number of states existing, and you are able to manipulate all these things for quantum computing. I think I'll continue. This is the quantum chip, definitely. Now, when we talk about the quantum, let me start with some basics, maybe overlapping. That's what I mentioned earlier. So this, I think you are hearing my voice. Is everything fine? Because
Yes, sir. Everything's fine, sir. Please continue, sir.
yeah, this is very, very difficult way of giving talks like this. You all know this has been going on for 2 years now. We don't know what the audience are doing, whether they are hearing or whatever it is. It's left to you. Now, quantum optics is the branch of atomic, molecular, and optical physics dealing with how individual quanta of light, that is the photon, interact with atoms and molecules. Okay, that the quanta comes from that point. And you all know in basic physics that light has a dual nature, as a particle as well as a wave. So I think wave concepts, a lot of applications we have realized, particle nature, and now the particle nature is being exploited for computing and so forth. So hello, like ನಾನು ಸ್ವಲ್ಪ ಒಂದು ಟಾಕ್ ಕೊಡ್ತಾ ಇದ್ದೇನೆ, ನೀವು ಅಲ್ಲಿ ಬನ್ನಿ, ಬರ್ತೇನೆ. ಒಂದು ಟಾಕ್ ಕೊಡ್ತಾ ಇದ್ದೇನೆ, ಅದು ಮುಗಿದ ಮೇಲೆ ಬರ್ತೇನೆ. ಬರ್ತೇನೆ. Sorry for the disturbance. Okay, and it includes the study of particle properties of photons. Definitely, photons have been used to test many of the counterintuitive predictions of quantum mechanics, such as entanglement, teleportation, and are useful resources for quantum information processing. So this is where the quantum computing is exploitation of collective properties of quantum states, such as superposition and entanglement, to perform computation. The devices that perform quantum computations are quantum computers. You see, you are trying to exploit the quantum properties, that is ultimately the photon, and try to do whatever the classical computers or classical systems so far we have been enjoying. Okay, and you all know, see, this the memory and the speed, they're always in demand. and the technology and the research are always working towards achieving that one, and that is now the quantum. Now, let me start some introduction. I think Srinivas might have used some of these slides as well. Okay, quantum computing is a type of computation that harnesses the collective properties of quantum states, superposition, interference, polarization, spin, entanglement of photons to perform calculations. And the study of quantum computing is a subfield of quantum information science. All go together. Okay, there are several types of quantum computers, okay, including quantum circuit model, quantum tuning machine, diabetic quantum computer, one-way quantum computer, various quantum cellular automata, automation. The most widely used model is the qubit. I think I don't repeat the same thing. The qubit, which is somewhat analogous to bit in classical computation. A qubit can be 1 or 0 in quantum state, and in a superposition of 1 and 0 states. When it is measured, always 0 and 1, the probability of either outcome depends on the qubit quantum state immediately prior to the measurement. This is very, very important concept. Okay, this is explained using the Bloch's sphere. He's a physicist, theoretical physicist. Bloch's theorem, we extensively use this in condensed matter physics. So this is how the quantum bit is explained. If you look at this Bloch's sphere, okay, this is a 3D sphere. The dimension is, you can talk about below 0.1 nanometer, and this is the quantum state. Okay, this hexagonals, this one you can see here. This is probability of finding this state within this sphere. That's where you can find the qubit, the concept of. Now if you look at the classical and the quantum difference, I don't know how these bits are compared with the classical bits. Okay, classical versus quantum bits. You see the classical one bit, either it's a 0 or a 1. If you look at it, it's like a coin, or it may be n bits repeating. Instead of this one, hello, enter. ಹೋಗು, ನಾನು ಟಾಪ್ ಕೊಡ್ತಾ ಇದ್ದೆ ಕಡೆ, ಆ ಕಡೆ ಬರ್ತೀನಿ. Hello? Hello?
Yes, sir. Yes, sir. Yes, yes, sir.
Get the here in a quantum bit, okay, qubit. If you look at the coins, it is tossed here. It is in this state, and in between there are states lying in. So 0 and 1, we can find millions of states in between. That's where the qubit. We are talking about problems suited for quantum computation. This is what I'm talking about, the security, the confidentiality. This ultimate achievement in quantum systems is as the speed and the memory and the security. I think still we have issues in terms of security of classical systems. You all know, anybody can still in this digital era, we always hear these problems. Somebody can hack your email, somebody can hack your credit card, and do all sorts of things. And these are all the things we every day hear in the newspaper. And ultimately, the quantum is a solution where nobody can tap anything and exploit in any situation. And how to realize a quantum computer is a big question mark. Partly things have been achieved, and it has been shown here that these are all the things where nano fabrication techniques are being exploited to do many of these quantum operations. That is through photon, ultimately through some physical system has to be there to exploit the concept of quantum through photonics. That's where the link between quantum and the photonics. It's definitely the photon that play a key role, and how to manipulate the photons through physical systems is the concept, and the theories are definitely realized, but practical realization through this is a challenge really. That's where I talk about something on qubit, the photonics components for quantum systems or quantum applications. So this is where standard computers, how they work, on these classical bits, on and off, and logic and the memory, and they are done through the semiconductors. These are processors, logic and the memory. It is here. Then together they form the computer. This is the computers from last 70, 80 years, more than that even. We have been using this technology, and we have, the world is so much used to this one, and the life is on these things now. Now, quantum bits, okay, you see here 0 or 1, and here's 0 and 1. Okay, superposition of both the states. I told, okay, quantum two-level system, atoms and the spins you are talking about, and here how the bits are. I think Srinivas has talked about all these things, how these are created in this block sphere, and these are enormous. This thing, and here the bits, qubits, the classical and the quantum bits, how they play, how the options are, and need 2n classical bits to encode the same amount of information in n qubits. Okay, so that's the limitation. And the important thing here is the measurement limits you. See, after the measurement, quantum state collapses, information is lost. This is where, see, this is where the advantage with quantum computing systems. So this is the in-between state of the photons. Okay, it may be polarization, spin, entangled states, superposition, all this. Once the measurement is done, the system collapses. So it is the advantage, means you cannot hack, trap anything. You in between, nobody can do anything, and this is the advantage. Now let us physically understand what is this superposition, how it is advantageous in quantum applications. Okay, one is superposition. This is the I just showed, it's a block sphere here, and the classical bit is 0 and 1, and the qubit is anywhere in between. Okay, this within this block sphere. In superposition, quantum particles are a combination of all possible states. Okay, this is what the superposition. They fluctuate until they are observed and measured. One way to picture the difference between binary position and superposition is, imagine a coin. Classical bits are measured by plopping the coin and getting heads or tails. However, if you were able to look at a coin and see both heads and tails at the same time in the tosser condition, okay, as well as every state in between the coin would be in a superposition. This is how the superposition is explained. And another one is the entanglement. Okay, this is very, very important, how the photons can be made entangled. So this superposition and entanglement are closely correlated. Okay, see, entanglement is the ability of quantum particles to correlate their measurement results with each other. When qubits are entangled, they form a single system and influence each other. They can use the measurements from one qubit to draw conclusions about the others. By adding the entangling more qubits in the system, quantum computers can calculate exponentially more information and solve more complicated problems. This is where, see, two qubits and they are influencing each other. Okay, that's how the entanglement is formed. Then the other concept is the quantum interference. See, this is where they are entangled. When the states are overlapping, then they are called interference. Okay, this also being exploited in quantum systems. So quantum interference, I'm trying to give the physical picture of all these things. Okay, so mathematically you can write, but physically how they act, how they perform, how they are being exploited, that is equally important. Now, quantum interference is the intrinsic behavior of a qubit due to superposition to influence the probability of collapsing one way to another, okay, or the another. Quantum computers are designed and built to reduce the interference as much as possible, reduce the interference, and ensure the most accurate results. To this end, our microscope uses topological qubits, and okay, there are different ways of manipulating all these things, and this is still developing, still highly confidential. Okay, theoreticians have also hundreds of solutions for these things. Then This is very important. Quantum entanglement is a physical phenomena that occurs when group of particles are generated, interact, share spatial proximity in a way such that quantum state of each particle of the group cannot be described independently the state of the others. See here, when I talk about a particle, it is nothing but photon. Okay, we are all talking about particle nature of the light. This is a very important concept, and generating, that's what I'm going to talk in future slides, that is how to generate quantum entanglement, single photon and quantum entanglement, the two photons. The topic of quantum entanglement is art of okay, at the heart of disparity between classical and quantum physics. Entanglement is primarily a feature of quantum mechanics, lacking in classical mechanics. Measurement of physical properties such as position, momentum, spin, and polarization from on entangled particles can, in some cases, to be found perfectly correlated. This is where the concept of entanglement comes. How to generate entanglement? See, they are not naturally entangled. Photons cannot be entangled like that. So you can generate entanglement, then use these between states for quantum computing. That's the whole idea. See here, one example is also given there. If a pair of entangled particles is generated, that is what I'm talking about, such that their total spin is known to be zero, and one particle is found to have clockwise spin on first axis, and the spin of the other particle measured on the same axis is found to be counterclockwise. This is where they are slightly the in-between states are existing. Okay, one is in the clockwise, another one is anti-clockwise. The generating of this entanglement is a challenge in practical situations. So this is where the real photonics comes. Okay, the photonics is closely connected to the quantum, and how to generate entanglement and how to measure these things. Okay, generating and make sure and justifying that these are entangled, and whatever the theoreticians are predicting, that has to be justified through the experiment, and make it simple. See, if you look at the experiments, you can demonstrate on the table, but they are not easy when it comes to the manufacturing. That's again long way to go. Now, this is quantum communication. Another, see, these are all part of quantum only. See, what is quantum communication? You all know that. Okay, sensitive data is typically encrypted and then sent across optical fibers and other channels together with the digital keys needed to decode the information. The data and the keys are sent as classical bits in a current state of the art communication. This is what is happening. So a stream of electrical or optical pulses representing zeros and ones, and then makes them vulnerable. Smart hackers can read and copy bits in transit without leaving a trace. This is where the problem comes with the classical communication systems now, optical communication system. In quantum communication, takes advantage of laws of quantum physics to protect data. These laws allow particles, typically photons of light, for transmitting data along optical cable to take on a state of superposition. This is where I talked about where the superposition comes. So beauty of qubits from a cybersecurity perspective is that if a hacker tries to observe them in a transit, their super fragile quantum state collapses to either 0 and 1, and nobody can hack. This is the advantage, one of the important advantages with quantum systems. Okay, so this means a hacker can't tamper with qubits without leaving behind a sign of the activity. Some companies have taken advantage of this property to create networks of transmitting highly sensitive data based on process called quantum key distribution. This is very, very important. This quantum key distribution is another important field of research, and different companies have their own QKD systems, and that is another big field. I will just give quantum, some basics of this quantum key distribution. So this is well established with the quantum key distribution is BB 84. Okay, that QKD involves sending encrypted data as a classical bits over networks, while the keys to decrypt, decrypt the information are encoded and transmitted in a quantum state using qubits. Various approaches or protocols have been developed for implementing QKD. A widely used system is BB84. Works like this. Imagine two people, Alice and Bob. Is a standard way. Is a receiver. Is the source. Alice, he wants to send the information to Bob. Alice wants to send data securely to Bob. To do this, she creates an encryption key in the form of qubits whose polarization states, this is another one, okay, they are using it. Polarization states represent the individual bit values as the key, and the qubits can be sent to Bob through fiber optic cable. By comparing the measurements of the state of the fraction of these qubits, the process known as key shifting. Okay, Alice and Bob can establish that they hold the same key so that they can decode the information. Okay. As the qubits travel to their destination, the fragile quantum state of the sum of them will collapse because of the decoherence. Okay, once the information is sent in between nothing. To account for this, Alice and Bob next run through the process known as key distillation, which involves calculating whether the error rate is high enough to suggest that a hacker has tried to intercept the key. So they can track it. This is where the visualization of the quantum qubit system. This is again quantum internet again. It sounds same. So whatever the applications you have seen in classical systems, we can realize all this in quantum systems. The quantum internet, I think you can see here. What this picture talks about, this is the block system, that the quantum states available here, quantum states available here. Okay, just like traditional internet, this would be a globe spanning network of networks. And the big difference is that the underlying communication network would be a quantum one, and it is not going to replace the internet as we know it today. Okay, and music, photos, great deal of non-sensitive business info is still move around in the form of classical bits. So this is a long way to go to replace the current state of the art internet through quantum, but there are chances in the revolution of this system as well. Okay, but quantum internet will appeal to organization that need to keep particularly valuable data secure. Okay, uh, now again, quantum repeaters. This is also equally important. In optical communication systems, we need repeaters. Okay, you all know that this EDFs, okay, fibers, they are put in between the stations when the optical signals go deep. Repeaters enhance the optical signals and they are transmitted. I think this is also needed. This is a prediction quantum repeaters. These are all the possibilities. And again, quantum teleportation. Okay, this is again, this may sound like science fiction, but it is a real method that involves transmitting data wholly in a quantum form. The approach relies on the quantum phenomena known as entanglement. So quantum teleportation works by creating pairs of entangled photons and sending one of each pair to the sender data and other to a recipient. So open space quantum transportation that is demonstrated. Okay. So okay. So this is when Alice receives an entangled photon, she lets to interact with the memory qubit that holds the data she wants to transmit to Bob. This interaction changes the state of the photon, and because it is entangled with Bob's, the interaction instantaneously changes the state of his photon too. So this is possible. Here is a table of comparison to quantum to classical computer, and there will be a parallel comparison for whatever you use, because quantum systems I mentioned, maybe once this is realized, quantum computer, quantum communication, quantum cryptography, quantum internet, all this will have a parallel comparison like this. So it's a large scale integrated multi-purpose computer CPU, and it is high speed parallel computer based on quantum mechanics. Information storage is a bit based on voltage and the charge. Information storage is a quantum based on the direction of an electron spin or electron transition. That's a photon here. So computer runs on the bits that have value of either 0 and 1. Here it is a quantum bit. This all I just explained. Discrete number of possible states, 0 and 1. Okay. And deterministic. This is a deterministic. Repeated computations on the same input will lead to the same output. Infinite number of possible states. That's where
Sir, you are muted, sir. Your microphone is muted, sir.
is it okay now? Hello.
Okay, sir. Now, please continue.
Quantum answers, which are in quantity called amplitudes, are the probabilistic, meaning that because the superposition of and the entanglement multiple possible answers are considered in the given computation, and circuit behavior is governed by classical physics. Circuit behavior is governed by explicitly by quantum mechanics. This is the main difference. Operations are defined by the Boolean algebra, and operations are defined by linear algebra over Hilbert space and can be represented by unitary matrices and complex elements. No restrictions exist on copying or measuring signals. Severe restrictions exist on copying and measuring signals. This is where the future systems are requiring. The circuits are easily implemented in fast, scalable, and macroscopic technologies such as CMOS. Okay, and circuits must be microscopic technologically that are slow, fragile, and not yet scalable. Long way to go. Nuclear magnetic resonance to understand the spin, and definitely a lot of nano fabrication techniques to fabricate all these components. This is okay. Look at how the quantum system works is first activate the spread of the states. Okay, encode the problem. That means you put the data into the activated states, then transmit it or process it, then unleash the power and the solution. This is how the quantum system works here. Okay, original state, encode the data, transmit or process, and get the answer back here. Okay, this is very important here. See, one promising quantum algorithm that uses these techniques is called Grover's search. Okay, there's a concept how to get the information back. Suppose you need to find one item from the list of n items. On a classical computer, you would have to check n by 2 items on the average, and it's the worst case. You would need to check all n, okay, n by 2 or n. You look at the n by 2 or now using Grover's search, the quantum computer, you would find the item after checking through only root n. See here, you see root n the system. This represents remarkable increase in the processing efficiency. Okay, and the time is saved. Okay, so for example, if you want to find one item, a list of 1 trillion, and each item took 1 millisecond to check. This is where now that's what in general you can scale it up. Classic computer, what they take about 1 week for the processing, the quantum computer can in 1 second. I think this is the prediction using the systems. Now I'm key photonic components for quantum. This is where I am going to mainly concentrate. Okay, how to achieve all this uh, quantum system or quantum application, maybe computing or communication or internet or cryptography, whatever it is. So key photonic components are the heart, the very important things in building quantum systems. So what are these? The single photon sources or sources of entangled photons. This is very important. How to generate? It's not as simple. We know all this. LEDs, I think we all may be very knowing in communication systems. You have a light source. You don't have about single photon. A light source may be a laser or an LED. You want to, so you know that 5 laser source you have in 850 nanometer on 1330 or 1550, that is enough. And you all know how the communication systems are built, and at the end detectors at the other end, and in between the repeaters, these kind of things, and optical fiber that makes the communication system altogether. But for a quantum system, what we need is a single photon source, or the source of entangled photons, and single photon detectors and fast response detector. These are the two things. And what you exploit here is again the polarization, momentum of the photon, spin of the photons. This is very, very important, how to detect this one. Okay, maybe polarization I can do, momentum of the spin, this photon and the spin photon. These are very, very important things to measure practically. See, this makes the limitation more severe. It means I think I don't say it's not possible, and all over the world people are working, and many people have developed many systems, many experimental setups are all demonstrated at the research level, and some are maybe in the practical utility level. I don't know. Definitely, what the IBM is talking, the quantum computers are ready to market. That's what they are talking. Maybe there also we don't know the this commercial systems. And then is the quantum key distribution. That's what we mentioned. Even every company or every industry has its own quantum key distribution. This and to connect all these things in between, waveguides, optical fibers, and the free space. Okay, these are the all are photonic, definitely photonic component. They require to build any of the quantum systems or any of the quantum applications. So this is how I told in the beginning before how the photonics is connected to quantum. Now, if you look at these semiconductor-based single photon sources, okay, now it's very, very challenging to build an institute. That means you know the semiconductor lasers. Okay, there are hundreds of types of semiconductor lasers. Definitely, it is not silicon. Many of the compound semiconductors, because there are some restrictions with silicon. So 3-5 compounds are extensively used for making laser diodes. And for a single photon semiconductors, for single photon generated on the sources, semiconductors extremely promising as single photon sources, and there are a multitude of materials that produce effective photon sources. For a single photon emission, quantum dots, specifically quantum dot space 3-5 semiconductors attracted a lot of attention in recent years, and there are many materials that form functional and often quite high performance single photon emitters at cryogenic temperatures. You see, this is very important because you can make hundreds of single photon sources, but temperature, say you know the dimension of a laser diode, it will be around hundreds, even less than that microns dimension. Okay, maybe 100 micron length, 5-10 microns width, and 10 microns height. Is a rectangular structure, and a 1 degree of temperature will lead to a lot of difference in the laser diode performance. So these emitters have to operate at cryogenic temperatures. Okay, they include helium gallium arsenide, aluminum amosite, and among others. Several materials are under investigation for room temperature based application. This is very important. And on quantum dot single photon source operating at 300 K using gallium nitride, the base material, and fabrication of such material under constraint of integratability on photonic environment is providing to be a considerable challenge. These are the, you all know, see, for any of the integrated optics, we talk about silicon photonics. But to making a light source on silicon is not possible. You have to go for 3-5 compound for making a light source. Then how to integrate this on silicon is again a challenge. So this is the problem in fabricating these semiconductor-based single photon sources. This is a laser diode source. We can make a what I can say is an in situ single photon source using a semiconductor laser. Now there are other things like single photon source. I can show this all follow standard semiconductor fabrication processes. It's okay, silicon, okay, wafer, then there are MBA growth of silicon with other materials. This is the waveguide, okay, and this is a fiber couple, and you have a this ring resonators. There are various other ways to make a single photon sources fabricated on a 3-5 compound and with other integrated optics. That is very challenging. You can make the single photon source taking a multi-photon source and externally using other optical arrangements. Okay, now you can create a cavity with a color filter, and see, this is the light source. Okay, and it's a multi-photon light source. You have a pump laser coming here, you have the filter, you are creating a cavity such that a single photon comes out and coupled with optical fiber. So this is one way of doing externally the single photon source. Okay, now another one is the entangled photon. So single photon source, I just mentioned, either you can make it a single photon source, putting all the conditions of low temperature controlling the temperature such that you can generate single photon force directly from the semiconductor sources, or you can make the single photon through the multi-photon sources, then do some external optical arrangement to make sure that there is a single photon source coming out to the optical or quantum processing. Now another one is entangled photon pair. Okay, particularly the polarization entangled photon sources are vital resource for generating non-classical states of the light. Typically, photon pairs are created by current pumping of non-linear crystals. The process is known as spontaneous parametric down conversion, SPDC. Okay, this is okay. These pairs are then entangled by coherent superposition of two orthogonal SPDC process in an interferometer. Entangled and entanglement and entangled photons have been exploited in several areas of quantum optics research, including computation, metrology, and cryptography. You know how they look like. You see this is the laser beam, definitely a multi-photon laser source. You use a non-linear crystal. It may be KDP or barium beta borate, BBO, and you generate two vertically polarization, this one photons, horizontally polarized photons. Then you can see the entanglement of the photons. This is done externally. So this is one way of generating entangled photons. Okay, now spontaneous parametric down curvation process can split photons into type 1, type 2 photon pairs with mutually perpendicular polarization. They are entangled here. This is one way of generating entangled photons. That is how practically done. Now this is, I just mentioned here, this is a tensifire laser source, and you have a band pass filter. This is a type 2 BBO crystal. This is beam splitter, wedge, okay, piezo actuators, and again here water wave plate, again a beam combiner here, and you see the two entangled photons coming here. So this is another way of doing it. So there are ways. So these are all very, very higher end experiments. Definitely I have not tried. And this is how the entangled photons are measured. Ultimately, you measure the intensity, plot it, and see the photons are entangled and compare with the theoretical predictions. Now, if you look at here, it's again a ring resonator. You have sources, and you can generate entangled photons here. Okay, this is the source coming here, and this is vertically polarized, horizontally polarized is coupled here, and this is coming and coupled here. You can see the entangled photon here. This is another way of doing, and they're all very complicated. I think this is again, I think Srinivas also might have used this one. This is BB 84 protocol for using this entangled photons. You look at the way here, light source here, release here, and you can, this is a vertically polarization, horizontal polarization. This is a 45 degrees, 35 degrees here. You can transmit all these bits, entangled photons. And see, the advantage here is in between nobody can tap this entangled system, and we cannot get any information here. And anything is tapped here, this Bob can come to know, or this Alice also can come to know. Okay, this is how it is done. Now, don't worry about this. Is how the polarization. This is vertical polarization. This is hello. And how it is done, you can see as I think somewhere this sliding, this is, they can use in between polarization states. Okay, this is how it is done. Now with the space division multiplexer system also, one can use single photons. You know that in space, this one using space division multiplexing, okay, wavelength division multiplexing, you can see the mode, single mode, multi-mode. This are also one of the ways of generating single photons or entangled photons. They're very complicated and tunable optical chip wave new quantum devices. These are all, you can see different ways of using the integrated optical chips to generate either entangled, single photons, all these things. So, and now photon counting detector. The second part is very important, how to detect a single photon. Single photon counters are very, very, I think the state of the art is already there, single photon counters. Now coming up with the nanotechnology, I think there are single photon detectors are already fabricated. Okay, human eyes are sensitive down to few photon level. Okay, 40 multiplier photocathode, okay, dynamic multiplication. This is one way of 40 photo multiplier tubes are there for many years now. They are capable of detecting single photons. Again, these photomultiplier tubes have to be operated at very low temperature. When 1 degree of temperature variation will lead to wrong data of measuring single photons. And semiconductor single photon avalanche photodiodes are also available. They are all operating at very low temperature. Okay, then superconductors. Okay, numerous detectors, for example, including superconducting nanowires. These are the latest state of the art of detecting single photons. I think superconductor nanowires. You can see how the single photons can be detected. Okay, this is photon counting detectors. Okay, this is where I just mentioned. And this is how the photomultiplier tubes work, a single photon, and it detects, okay, when you apply voltage between these anodes of the diodes, it is multiplied. Finally, you can detect a single photon. And photon counting detectors, okay, this is again a very complicated CMOS process of generating silicon photodetectors. And so this is the state of, I think these processes are well established in semiconductor industry. I think definitely they can be done. Then superconducting nanowires, you can see, I just showed in the previous image. These nanowires react to, see, nanowires, as I mentioned, the dimension is about 5 to 10 nanometers. Length is 1 or 2 microns. The diameter I'm talking about, definitely they respond to the single photon and easy to detect. Now single photon detectors, okay, visible infrared in this range, they have to operate. Okay, now if you look at this, okay, single photon detectors applications, okay, film and quantum optics, free space radar, IC testing, and quantum cryptography in fibers. Okay, atmosphere sensing detectors of photomultipliers in this range, IRPMTs, silicon single photon, halogen photodetectors, gallium nitride, varieties of superconducting detectors. These are the ranges. See, characteristics of single photon detectors is uh, is very important. High quantum detection efficiency at wavelength of interest, probability of noise triggers, dark counts, time between detection of photon and generation of electrical signal should be constant, low jitter. You see, very, very important. You are measuring single photon and the response time should be in nanoseconds or even picoseconds. Otherwise, you will not be able to detect. Short recovery time, that is red time for single photon, one single photon to second single photon measurement. The dead time should be very, very small. Ability to resolve the number, I think this is a very good review article one can read. And superconducting nanowires, again we can hello, key properties, wide spectral range. I think I have shown in the image itself. Superconducting nanowire single photon detectors are very, very useful because the spectral range is very wide, free running, no grating required, low dark counts, and low time jitter and short recovery time. Okay, this considerable scope for further improvements. I think this you can see. And superconducting nanowire single photon detector structure looks like this. Okay. Okay, look at the dimension I talked about. You see, this is the 3.5 nanometers. Okay, this is about 100 nanometer. So you, on the top of it, you can measure, bias current here. Photon comes on the top. You can measure the voltage drop, and that's how the system works. Okay. Okay, hotspots, this is bias current. Okay, this is how it is measured. Okay, then this is a single nanowire. Okay, single nanowire detection. Okay, these are all very, very complicated structure. This have been realized long back. I think the technology has gone somewhere now. I'm not going to talk much on this one. Single layer, meander, optical cavity, varieties of superconducting nanowire structures can be fabricated, and they are realized, and they are being used now. With single photons, okay, quantum systems can be used to encode, manipulate the information. The dramatic improvements in secure communications, metrology, and computation. Okay, then in principle, many candidate quantum systems trapped ion spins in semiconductor quantum dots, superconducting circuits are also being explored. Okay, optical photon makes it ideal flying qubit. These are all the advantages with photons. Definitely, it is. The photons have low decoherence even at room temperature, easy to route, manipulate. Okay, this is how polarization of photons is being exploited. This is horizontal, vertical in between the states from horizontal to vertical and back to the same system. Okay. Okay. This is the advantages have an important role in new quantum information system application, characterization of quantum emitters, quantum key distribution, operation of quantum waveguide circuits. Okay, these are all things. Now the quantum emitters and quantum detection, this is very challenging to see how to see that whatever you are seeing is a single photon, whatever you are detecting is a single photon. So this is a very challenging experiment, and I don't think in India very few labs, maybe one or two labs have some facilities to do these kind of experiments, single photon and sources utilize, they use generating single photons and also detecting single photons. Okay, these are some of the experiments these people have done long back. Okay, very delicate experiments. See, this is again measurement of a single photon coherences. I think some of you, I don't know whether you have tried or not. Again, long wavelength characterization of quantum emitters using. See, uh, uh, the demonstration of the, you see the complications involved here. First of all, one need to demonstrate the source you are using is a single photon, and make sure that this just directly emitted photon from the source. Then you make sure that what you are detecting is a single photon. Now in between these two you have the process. Okay, the QKDs. Okay, then other types of exploiting the photon properties may be momentum, spin, polarization, and it may be a single photon or it may be an entangled photon. If you make sure that your source and your detection system is perfect, then you will be able to establish that the processing is done, whatever the quantum process you are doing in between is right. So I think I have not done this experiment, that's why I don't talk too much on this one. I realize the complications involved here, but I have seen the people working on this, and I understood from them that it's a very complicated experiment. However, it has reached some stage. Okay, and so there are very complications in between. I mentioned about certain error rate, threshold, secure key can no longer be generated. There are two contributions to the error rate. See, I told single photon source, single photon detector. In between, what is happening? These are the things one has to do. Okay, fixed 1%. This is where they talk about. Okay, distance, shift, all switches. Now superconducting nanowire single photon detectors in quantum key distribution. And again, you have to select the wavelength. Superconducting nanowire single photon detector benefits from QKD in optical fiber, single photon sensitivity, and okay, the transmission in between, it's the process and the transmission. These are the two issues coming into once. When it comes to transmission, you are using a 1550 nanometer. When it goes to optical fiber, you have to use that one only. So then low dark counts you need to have, low emitting timing jitters. Okay, Gaussian instrument response function. All these are very low level detection techniques that is required, and ultimately one has to long distances, high bit rates, for the communication. Now I think I am showing some groups experimental arrangement for a single. Okay, first QKD demonstration with single this one okay, superconducting nanowire single photon detectors using a quantum net. This is a demonstration long back, and how the complications arise in the experimental arrangement. Okay. Minute. Are you okay?
Yes, sir. Please, sir. Continue, sir.
Now you see free space, new directions in QKD, ground to space. Okay, this is where I think India is moving forward. I think some people have demonstrated. I think ISRO and some research groups have demonstrated of hundreds of meters of free space communication using quantum systems. Sorry, I think I have skipped some of these things. Okay, and I think we are somewhere photon flux, how the micro lensers. See, this is where cavity enhanced nano air pixels and micro lens array. These are all the photonics devices being utilized in quantum systems. That's where the whole of my talk is focused on. So whatever you do in nano photonics components that are very much necessary for quantum systems development, and this is where the things are moving. And again, after the quantum single photon, entangled photon sources and the detectors, I think in between for the transmission, whether a free space or the basic waveguide geometries, you all familiar with this fiber, okay, or channel waveguides for a chip in the processing for the quantum computers. This is very much, this is the quantum communication. You need all these things for a quantum chips. You need to connect the sources through the waveguides within buried waveguide, strip loaded waveguides, embedded waveguides. These are the systems and integrated circuits on silicon. These are possible, and this is how the in integrated optics you can see how the light travels from one location to another location on a silicon chip. I think in a similar way. Uh, for us now quantum systems, single photons have to travel from one location to another location. The silicon chip, again, this is one more challenge, but these are all possible. I'm talking about quantum waveguide systems through fiber CK optical waveguide circuit can be used to replace conventional optics. Okay, this is, you can read all these articles somewhere. They are available how to make the waveguides that can support a single photons. This is again a challenge in making photonics components for quantum computing and operating quantum waveguide circuits with this is again another group they have done. So a lot of single external systems can be built to understand the concept of these things. Okay, again, single photon sources, single photon detectors, but to develop this on an optical chip is really very challenging. And okay, this is how applied physics letters people have published. I have taken all this from those operating quantum waveguide circuits with migrating sorry quantum waveguides circuits with single superconducting nanowires. These are the talk of the year. This systems are coming up, heralded source for fast lithium niobate systems. Again, these are all the the varieties of optical materials are being explored. Like silicon has certain advantages, at the same time certain limitations. From the fabrication point of view, silicon is one of the best photonic material for developing many of the quantum components. However, it has certain limitations. That's why people are looking for alternative optical materials. One of them is lithium niobate. Okay, this I think we also have tried lithium niobate for various components, photonic components development, and this has another problem because the silicon uh, uh, fabs, they don't entertain this lithium niobate. Lithium niobate has to be fabricated on a separate fab. I think that's where the problem comes. That's why in India we think we are not able to fabricate this lithium niobate in silicon fabs. There are many companies in the world. They have established separate labs for processing lithium niobate. I think if that works, I think many of the limitations which we have with silicon that can be replaced with lithium niobate. Fast switching and quantum interference. Again, this is realized. Okay, I'm not going to the detail. This is how single photons are detected. Okay, yeah. Quantum interference explanation here now. Steps to build a quantum computer or any of the quantum applications we have talked so far is it is like this. Okay? Operations on single physical qubits, algorithms on multiple physical qubits, QND's measurements, okay, quantum system measurement for error correction and control, logic memory with longer lifetime than physical qubits, operations on a single logical qubits, uh, algorithms on multiple logical qubits, fault tolerant quantum computation. So I think there are some more to come. All this lead to now coming back to this is how the steps on building these things. And see, academics have their own limitations. And see, particularly in this field, academics have their own way of bringing the system up, and the advanced companies have their own way of bringing the system, the operation. But for all these things, the limitations are on the, I showed in the first slide itself, the most law. One is the the fabrication limit to bring it to the manufacturing limit, this one level. I think we have hit, this means the like E-beams fabrication techniques. So you can go up to 10 nanometers so far. One can fabricate the structures with 10 nanometer feature size. And again, using the same technique for making the sources and the detectors, and the quantum levels sensitivity to other temperature or any other physical or environment variations. That is another complication. And this, if the fabrication and overcoming all these limitations, definitely one that means the realizing these quantum computers on the table, maybe, I don't know, taking few more years in the line. We may realize all these things. Even though we talk all these things, maybe some companies have built already and they are looking for the right time to really realize and see this, and long way to go. However, definitely like China and US and Japan maybe, and some of the European countries are in the forefront of this research as well as the technology development. India is slowly moving in that direction, but I still have a doubt that India will pick up this one in shorter times, because still we are not able to make our silicon based process or the CMOS technology. That is, I think we are already 60 or 70 years behind in that direction also. But the government is encouraging so much to start because of the chip shortage. This government is inviting companies, why can't you start manufacturing chips, silicon processes or silicon CMOS chips fabrication in the country. If we are able to do that one, maybe in next 10 years, then we go to the quantum and all integrated optics. Let us be hopeful in that. That means we have a big challenge in future to see anything here. With this, I think I will stop here. It took around 1 hour 15 minutes. Yes, started at 11:45 and I'm stopping at exactly 1 o'clock now. Summary is here, an overview of quantum computing idea is given. And as I told in the beginning itself, I am not an expert in the area. Do bits and pieces here and there, but as a quantum computing, I think I have given some idea. That's all. Photonics components required for quantum for computing, quantum information processing is just provided. I have not talked about the overall uh, techniques to make these components. Really, it's a separate field altogether. Making a single photon source or single photon detectors or waveguide fabrication or other integrated optical components like ring resonators. I think this itself is a separate 1 hour talk how to do that one. Then a brief introduction of photonics experimental and practical arrangements has been presented. That's what I gave. All these experiments are very complicated, very challenging experiments. I think with this I will stop here. You can ask if you have any questions. I can answer. And thank you once again. Let me go back to the this thing. Okay.
Okay, thank you so much, sir. You have given in detail about quantum computers and how these measurements limits and semiconductor-based single photon sources and photon counting detectors. And finally, you have explained the summary about these steps for quantum computers and all. Very nice talk, sir. Any questions from participant side? So it's time for questions.
Hello.
Hello.
I
Hello.
have a question.
Yes. Welcome. Sorry.
Sir, I want to just quite understand how, what is the state of creating a quantum computer that the big industry players like Google and others are creating? Any research on building that or the hardware side of it, like that
Yeah.
can simulate quantum computing phenomena that we are seeing here?
Yeah. I think that means Google has claimed, even IBM also has claimed some maybe 1 or 2 years back they're already using the quantum computers for processing. That means they are using it already. They are not no, given it to any no users or anything, but they have demonstrated and they say they are using it. That means they have fabricated or whatever things which I have shown. They have already done. They claim, but whether it is useful for the maybe these are used for maybe in US, maybe for some defense purpose and other things. They may be using it also. We don't know how confidential the issues are. They just talk about it, but for the outside world so far we have not seen anything for quantum computing or quantum information or quantum communication. But quantum processing, I think they say they have been already using it. That is the state of the art. However, from the research point of view, all over the world, people are doing definitely as a one lab it is impossible to build a quantum computer at all. However, some people are demonstrating qubits, some or the QKD system, some universities they are working separately, and some people are just working on single photon detectors, single photon sources like this. That has been, and some groups are just working on entangled photon generation, and some people are generating just space communication like space applications. This has been there, but it's a long way to go. Maybe 5 10 years 20 years, you don't know that a public can use the state of the art. I think it is still in a very infancy stage, I can say. Hope this will answer your question.
Any other questions from participant side?
Good afternoon, sir.
Hmm. Hello.
Thank you for the session, sir.
Hmm.
Sir, is my voice audible?
Yeah, I can hear. Please.
Yes, sir. Recently, I was researching more on this quantum cryptography. As part of this, I came to know about this counterfactual quantum key distribution.
Mm.
So, but I haven't found much research papers on it, sir. In 2009, by Thanago, he
Mm.
have invented this counterfactual QKD. So, will this counterfactual QKD will become the robust scheme currently, sir? Or
I
there
think
any other robust schemes exist?
that is the latest one. After that, very few QKD systems are available. I think 2 3 protocols we have been seeing that one. Okay, not much in that direction.
Yes. Yes, sir.
I think 2 3 which you have shown. Whatever you mentioned, that is the one latest. Not much of development has happened. People are using just the same whatever is BB84 and other 3 4 QKD systems are in use right now. Not much of the progress, because the progress depends. See, theoretical demonstration is one, but practical limitations are a lot, because they need to develop parallel components to process this or to realize these things. I think it is a level is same, not much of a progress as such. QKD systems.
But will that be the become the robust scheme, sir, if implemented? Because in
Yeah,
paper,
definitely. Yeah, that is expected. Yes, that's the ultimate robust system so far existing.
okay, sir. But actually, the author of the paper, Thanago, mentioned that proposed counterfactual QKD can be implemented using the available technology.
Yes,
So
exactly. I agree
yes,
your point. I also don't know much beyond that. I think that's what he has predicted, and it is going with that one only. Not much progress with developing new QKD systems. 4 5 systems are available in the literature so far.
okay, sir. Also, when coming to a single photon emitter, recently I
Hmm.
came to know that tungsten diselenide is best acting as a single photon emitter, sir. Is that true, or any other single photon emitters exist more better than that?
There are many single photon systems existed, but the there are various other conditions applied to them. Okay, because this material science is another big field where people are exploring varieties of compound semiconductors to make single photon sources or emitters. The challenge here is room temperature single photon emitters. So the realization is still not uh, uh, possible. Single photon in situ sources. The external way of making single photon sources is different. That is, there are varieties of schemes to do that. But single photon detectors at room temperature still has no challenge. There are some materials based single photon emitters, but the stability and long-term usage of these things, maintaining the temperature for a long time, these are all the persisting challenges. I think one day we can realize a stable single photon source for a long time at room temperature. This is a challenge, and this is open research.
Sir, then currently what can be considered as the best out of all single photon emitters, sir? What is the best? Which is
Uh,
acting as a best based on all those constraints you have mentioned?
with all these constraints, there are some silicon, not silicon, gallium, aluminum based single photon sources are uh, available. I think still I don't know which is the most stable single photon source, but definitely it's a compound semiconductor based source, and some sources with an integrated optics. It's a chip kind of. It's not just a source, but source integrated with the like ring resonators. That is the most stable one. Okay, integrated photonics with integrated source. That is the most stable one, rather than any material based single source. That's the most stable one. Integrated photonics, silicon single photon sources.
Okay, sir.
Okay.
Thank you, sir. Sir, when can we expect these quantum computers into the market, sir? Because when I was researching, my professors used to ask me, "You're telling some kind of a sci-fi movie to us." It was not.
Oh,
It,
very, it's a very difficult to predict. Maybe some future telling Swamis only can tell, because very difficult. Anytime it may come, or it may take longer time also.
uh,
Maybe then maybe next 5-10 years we may see at least as a university level or a defense level usage, not an individual usage of quantum computing systems. I don't think we may realize in shorter period. Okay. Organizations utilize, maybe defense, maybe some specialized fields of the sections can use, like a space application, these kind of things.
Sir, are there any institutions working on this QKD, sir? If
Oh,
research enthusiasts like me want to work there and explore more.
definitely. I think I can maybe I can give you list later. Maybe there are many groups working in different areas of this quantum systems. Okay, QKDs. I think if you can send an email, I can give some list of the universities who are working. Okay.
Okay, sir. Thank you so much, sir.
So right now, simulation environment is available now. So that we are working. Will it be correctly? Can we correctly simulate on the simulation environment provided by the IBM machine, sir?
Can you repeat? I cannot hear you.
Like we are working on this QSKIT environment provided by the IBM lab, sir.
Hmm.
So whatever simulation we are doing on this simulation tools, can we exactly correlate it for the working on real-time machines, sir? How will there be a difference, or those results can we append to our research papers like that, sir?
I think very difficult to predict, because you use a simulation with a quantum system. You use it now, right now. I think it may not be easy for you to do a simulation with a quantum system. You definitely, I think I have shown in some of the beginning slides, the simulation, quantum simulation is not it realized. I think maybe some places, universities may be using like for nuclear applications. Okay, people have been so far using supercomputers for energy estimation and these kind of things. It's a highly confidential things, but they are all using supercomputers. But it is not available for the public, whatever you say. But you can definitely do the simulation which you do with the classical computers. That can be done in fraction of a second of what you do in. That is, you can do a compare. I don't know where it is available right now. Okay.
Yes, sir. Okay. Right,
Okay,
sir.
but definitely, is this what the predictions are?
Yes, sir. Because sometimes we do, for example, bosonics environment or some kind of gates when
Yes,
we are
yes,
working.
definitely.
Yeah.
Definitely, it's a challenge. See, once you
Yes,
get
sir.
as a classical,
Comparison.
yeah,
Yes, sir.
whenever you do all simulations, you have always end up with some things, some problem. This cannot go beyond this. That's where the quantum comes. It is always
Yes. So when we write the results and all conclusions,
yeah,
I always get frightened to compare my results with the foreigner people, so many people like you who are really working on the real systems. And how can I boost that my work is at least equal to them, or greater than some kind of achievement outcomes?
yeah,
That somewhere I'm
definitely.
getting frightened to write that. So that's why I asked the question, sir.
Yeah,
Thank
really,
you.
it's a good question, because there is always that's what we have to see the limitations and stop it there only, because that's how the research goes. Always people are looking. Okay, even we realize here in with all the supercomputer facilities here, some of the one of the students who was working on the drug development for cancer or AIDS or something. He wanted to do a simulation. Actually, when we realized, we tried to run this one in a supercomputer facility, we couldn't get any solution till the end. Then we realized it needs a quantum computing facility, because that drug simulation is not easy. Okay. So then we realized that, okay, we have to stop at this point and come to a conclusion based on whatever is available. and it was taking for 15 days to compute that drug. Okay,
Yes.
that
Yes,
is
sir.
the level, because it's not an atomic, it's a molecular level. Then individual atom, then you integrate it with the molecule, then you connect it to the biology.
Yes,
So
sir.
this is the limitation comes. Okay, we couldn't run that simulation, but the directions were
Yes.
very clear that then if the resolution comes out of this simulation, you can design a perfect drug. The where you stop it. Okay, this is
Recently,
this.
I learned one more thing on the same cancer detection prediction, and also
Oh,
nowadays we're having these two-dimensional imaging tools, for example, maybe CT scan, MRI, or whatever is there. But suppose if we can pass this quantum material kind of things into the person's blood and all, then they are going to, if any cancerous cells are there, it is going to absorb that, and for much amount of time, that elimination we can see, and with a strong signal strength also, and that we could capture the like kinds of things I am reading in this quantum
yeah,
environment.
sure. Yeah,
So this and
yeah.
all we can't practice in a simulation tool. That's why
Correct,
my
correct,
report.
correct,
So,
correct.
yes, sir.
So all this can be addressed using quantum, systems. Hopefully, we will be able to realize in our life.
Yes, sir. Thank you so much, sir.
Okay.
Any other questions from
Sir,
participants?
sir, your mail ID, please, sir.
I think I have shown it. Gopal.hegde@gmail.com. I think Triveni is having it, or
Yes, we'll
gopalkrishna@iasc.ac.
share it in the chat box.
Okay,
Okay, sir. Thank you, sir.
okay.
Hope this session was very useful to all the participants. Thank you, sir, for being a reserve person with us. Really, this session was very interesting and a wonderful talk, sir. Thank you so much, sir.
Thank you.
But all the participants, feedback form will be shared at the end of the day, every day. Attendance we are taking in the Teams itself for each session. And the session 3 will be started at 2:30. Now, yeah, all of you can leave now. I will meet at 2:30.
Okay,
Thank you
thank
all.
you.
Thank you all.
Triveni, I will leave. Okay,
Yes,
thank you.
1 second, sir.
Thank you, sir. Thank you, sir. You know.